Welcome to numerical integration and substitution. This is finding the definite integral. So when we're finding the indefinite integral, right, we're finding the antiderivative. We're finding the function whose derivative is the integral. When we're doing numerical integration, when we're finding the definite integral, we're finding a number. That number corresponds to area under a curve. It also corresponds to the limit of Riemann sums as the number of partitions goes to infinity. And we know we can calculate it by integrating and then evaluating using the limits of integration. But what happens if we've used substitution to calculate, to determine the antiderivative? We have two choices. Choice one, after integrating, using a u substitution, substitute back for u and keep the limits of integration. Choice number two, after integrating, using a u substitution, keep u, but use u to change the limits of integration. And we're going to see both techniques used in the next two problems. And then I'm going to do some more problems, but I'll alternate techniques. All right, so here's our first one. We have the integral from 1 to 3 of 10x times 5x squared plus 6 squared dx. And we see we have something raised to a power. This is definitely a chain rule, and we can undo the chain rule with a u to u substitution. U is going to be what's raised to a power. Actually, I'm going to switch colors. All right, so u is going to be 5x squared plus 6. The derivative of u with respect to x would be du dx, and the derivative of 5x squared plus 6 would be 10x. Let's isolate the du. So du is 10x dx. We're going to replace the 5x squared plus 6 with u. We're going to replace the 10x dx with du. And that gives us our new integral. Now, I'm not going to put the limits of integration, right, because that's the limits of integration for x, not u's. All right, so we'll just leave them off, we'll integrate, we'll substitute back, and when we substitute back, then we'll put those limits back. All right, so we have u squared du. All right, nice, easy, undoing the power rule here. All right, so that would be u cubed divided by 3. Don't worry about the c, right, because this is numerical integration, right? We don't have to. We're not writing a function. We're finding a value, right? So we have u cubed plus 3. We're going to substitute back. The u is 5x squared plus 6. So 5x squared plus 6 divided by 3. At this time, I'll put the limits of integration back. So from 1 to 3. And then we can plug it in and evaluate. Right? So that's our last step, is to evaluate. So we have, oops, but don't forget, when we plug back the u, maybe because there's a 3 is one of the limits of integration, I almost forgot to put the exponent. Don't forget to put to replace the u, but don't forget the exponent. Right? That'll give us a really wrong answer. So 5x squared plus 6 cubed divided by 3. And we're evaluating that from 1 to 3. So we have 5 times 3 squared plus 6 divided by 3. And the u part is cubed, not the 3. And then minus 5 times 1 squared plus 6 cubed divided by 3. And it's a good thing I have a calculator handy, right? All right, so we have, that would be 5 times 3 squared, that's going to be 45 plus 6. That's going to be 51 cubed divided by 3 minus, all right, so we have 11 cubed divided by 3, which is so nice number, 132,651 divided by 3. And although this number is divisible by 3, there's no point because 11 cubed is not, since it's 11 times 11 times 11. I should know this one. It's a nice cool palindrome. 1331. divided by 3 is going to give us 132,651. So 131,320. Actually, I could have divided that. I could have subtracted that without the calculator. I had no carrying to do. 131,320. But I had the calculator handy. Divided by 3. And no, that is not divisible by 3. So that is our answer. All right. So there's the first one. All right. So here we simply substituted back, and then we evaluated using our original limits of integration. This time, we're going to change the limits of integration. So let's look at the next one. Same problem. So we know what the u is and the du, right? So u is going to be, of course, 5x squared plus 6, and du was 10x dx. Now we're going to change those limits of integration, right? So if x equals 1, so this is going to be, let's do the, we'll do the lower first. So this is the lower limit of integration. If x equals 1, then u, let's put it over here, then u equals, I'm going to simply plug this in for the u, right? So then u would be 5 times 1 squared plus 6, right? So we're calculating out a new limit of integration using the old limit of integration, but we're plugging it in for what u stands for. So now this would be, so that would be 5 times 1 squared is just 5, right? So 5 plus 6, that is 11. So now 11 is the lower limit of integration, and then the upper, if x equals 3, then u equals 5 times 3 squared plus 6, right? And so that's going to be 51. And those numbers probably sound a little familiar, right, from when we were calculating out by substituting back. All right, so now we're going to rewrite this, right? So now I can put the limits of integration because I'm using u's, and I'm sticking with u. So the lower is 11, the upper is 51, and this is u squared du. All right, so now we integrate, and we have u cubed divided by 3. And we're evaluating that from 11 to 51. There's no reason to substitute back because we've changed the limits of integration. So now this is going to be 51 cubed divided by 3 minus 11 cubed divided by 3. And we already know what that is, but I'm going to put right in the values. So 51 cubed, as a reminder, is 132651. 132651. Divided by 3 minus, and this one was 1331 divided by 3, and that gives us 131,320 divided by 3. That time I did it in my head. And you get the same answer, right? It's just a different technique, right? So if you don't want to change the limits of integration, then just substitute back, right? And once you substitute back, you can plug in the old limits of integration. If you don't want to substitute back, then change the limits of integration, and you don't have to, right? Both ways work perfectly well. So let's do another one, and we'll do both methods, and then I'm just going to switch on and off. All right, so method 1, we're doing a u to u substitution here first, and this is our integral here. The integral from 0 to pi 8 sine 2x to the 5th power times cosine 2x dx. The something to the power, of course, is our u. So u is sine 2x. The derivative with respect to x is going to be, derivative of sine x is cosine 2x. And then we have to take the derivative of the 2x part, right? So derivative of sine is cosine, and the argument stays the same, but then you got to take the derivative of the argument if it's not just at x. All right, so we're going to move the dx to the other side. So du equals, and of course the derivative of 2x is 2, so let's just write the 2 in there. So du equals 2 cosine 2x dx, right? But we have a cosine 2x, but we don't have the 2. No problem. We'll just make that 1/2. du equals cosine 2x dx. So we're going to replace the sine 2x part with u. We're going to replace the cosine 2x dx with 1/2 a du. Right? So let's rewrite this. And we have, and I'm going to leave off the limits of integration until we substitute back. Right? So we have 1/2 can go outside. 1/2 u to the 5th power du. We'll integrate. So that would be 1/2 times u to the 6th power divided by 6. Right? And that's equal to u to the 6th power divided by 12. Let's substitute back. Right? So u is sine 2x. Right? So that's, and now it's got a 6 there. Sine 2x to the 6th power divided by 12. Once we substitute back, we can put the limits of integration. So 0 to pi 8. All right, and so now we'll plug everything in. We've got sine 2 times pi 8. That whole amount gets raised to the 6th power, and then we'll divide by 12. And then minus sine 2 times 0 raised to the 6th power divided by 12. All right, so sine 2 times pi 8, we're going to look in the inside there, that's pi fourths. So now we've got sine pi fourths, all raised to the 6th power, divided by 12, minus, all right, so this would be sine 0 to the 6th power, divided by 12. Well, of course, sine 0 is 0. So this part here is 0. All right, so let's figure out the sine pi fourths. As a reminder, pi fourths is your 45, 45, 90 right triangle, right? Pi fourths is the same as 45 degrees. So 1, 1, square root of 2. Sine is opposite over hypotenuse, right? So sine pi fourths equals 1 over the square root of 2, or if you want to rationalize that, square root of 2 over, over 2. There we go. So let's replace the sine pi fourths with the square root of 2 over 2, and that is raised to the 6th power, all divided by 12. All right, so we got to raise the square root of 2 to the 6th power. That's the same as 2 cubed. So 8 in the numerator. And then 2 to the 6th power is 64. And then that's times 1/12. Let's just rewrite it like that. So now that's going to reduce. All right, so 8 over 64, that's 1/8. And then times 1/12 will be 1 over 96. And there's our answer. All right. We're going to do the same thing, but this time we're not substituting back. We're going to change the limits of integration. All right, so we, of course, know that u is sine 2x. And du, remember we were missing the 1/2. So 1/2 cosine 2x excuse me. The 1/2 is going to be on the other side, excuse me. 2 cosine 2x dx. We don't have the 2, so 1/2 du equals cosine 2x dx. All right, so now we're rewriting this. Before we do that, though, don't forget we're going to change our limits of integration. All right, so lower limit. If x equals 0, then u equals sine 2 times 0. All right, well, that's sine 0, and that is 0. All right, so there's no change there. And then upper. If x equals, I'm going to put a little then there so that you understand the progression. If x equals pi 8, then u equals sine 2 times pi 8, which is sine pi fourths, which we know from the other page is, I don't think I have to draw it again, right? Is the square root of 2 over 2. All right, so we have our new limits of integration, and we are going to not substitute back. So we have u to the 1/2, u to the 5th du, right? And then we'll integrate. And don't forget our limits of integration. So that is 0 is the lower, and the square root of 2 over 2 is the upper. So now we have 1/2 u to the 6th divided by 6, and we're evaluating that from 0. I'm just going to put a little parentheses there. 0 to the square root of 2 over 2. All right, so let's simplify. This would be u6 divided by 12, and we're evaluating that from 0 to the square root of 2 over 2. So now let's plug in. So that would be the square root of 2 over 2 to the 6th power divided by 12 minus 0 to the 6th power divided by 12. All right, so the square root of 2 to the 6th power, that's just the same as 2 cubed, and that's 8. 2 to the 6th power, that is 64. And then times 1/12, that's just 0 to the 6th power divided by 12 is 0. And that does reduce to 1/8 times 1/12, 196. So you see, you get the same answer. I do have my favorite, but you pick your own favorite. You look at them, as we're solving them, you try out both techniques, and you pick out the one you like best. All right, so this was a little introduction. In the next lesson, we're going to do a whole bunch. I'm going to alternate back and forth, but I'm not going to do every problem twice. All right, so bye for now. See you in the next video.